Good evening, oh curious audience wondering about the great mysteries of existence. Welcome. Welcome to Aloud. I'm a pleasure to see you here tonight. I'm Louise Steinman, the curator of Aloud and the program director for the Library Foundation. Give the Library Foundation a hand. Thank you. Jim Holt has said that his ambition in Why Does the World Exist was to see, quote, how far the human mind could go in penetrating the mystery of existence. And to do so, he set out to tap the minds of cosmologists, theologians, particle physicists, philosophers, mystics, novelists, and one Zen Buddhist priest who bopped the author on the head for such an impertinent koan. Tonight, he'll interview Sean Carroll, a Caltech cosmologist who was last on our stage discussing the nature of perception with Zen poet Jane Hirschfield. So you know Sean's always up for a challenge. Sean Carroll's research focuses on fundamental physics and cosmology, especially issues of dark matter, dark energy, and the origin of the universe. He's the author of The Particle at the End of the Universe and From Eternity to Here, The Quest for the Ultimate Theory of Time. Jim Holt is a longtime contributor to The New Yorker, where he has written on string theory, time, infinity, numbers, truth, and bullshit, among other subjects. His previous book, Stop Me If You've Heard This, A History and Philosophy of Jokes, posed another perhaps unanswerable question, what's so funny about humor? And he's a funny guy. In a beautiful review of Holt's new book, reviewer Michael Roth wrote, when Holt asks why the world exists, he is also asking whether there is any point to our being here. He is struck by the extraordinary contingency of our lives and of our world, and he seeks to address that contingency with theories about the emergence of time, causality, of something, but his real concern isn't creation, but extinction. Why some things turn into nothing. Why do we lose those we love? Why do important parts of our world vanish? These are not questions for a detective story, existential or not, but they are the questions to which, in the end, Holt's wonderfully ambitious book leads us. Though the ultimate answer tonight may lie outside of reach, Jim Holt's new book will help shape the conversation in time to come. Let's hope that we can gain some insight on the beginning and the end, and perhaps even find out where those missing socks go. Please welcome Jim Holt and Sean Carroll.
Very grateful for, I assume that was a very generous introduction. Did
Let's
we
just
come off
assume
well?
it was generous, yeah.
I'm delighted to be in Los Angeles, a city that still holds romance for me because I understand nothing about it. It's a mystery. It's as mysterious to me as the cosmos, which of course is our theme tonight. And I'm really happy to be on stage with Sean, who I've never met him before, but I've read his book for the second time, From Eternity to Here. And it's a masterpiece of, I mean, it's limpid in argument and in style, only 2 typos, which I pointed out to him backstage.
Within 5 minutes of acquaintance, he's pointing out typos.
And his new book, I can't vouch for that. It's probably not nearly as good as this, but this is fantastic. I commend it to you all. And it's philosophically very shrewd, and we'll get into, there's been a kerfuffle or a war or a battle recently between philosophers and physicists, and you're one of the good physicists. You think that philosophers actually have something useful to say, and I'm just a journalist, so I'm above the fray. I don't care. Anyway, so enough of this. We didn't come here to bandy chaff. We came to talk about the mystery of existence and all of that. So let me just begin by asking you a question, and I want you to answer this in one sentence. He has a reputation for gassing on, so you have to give him a word limit. And the question is, what does reality consist of? At its most basic.
One sentence. Reality is a quantum wave function evolving through time.
Okay. I knew he was going to say that. You walked into a trap.
I said that.
Tell us what a quantum wave function is.
So there's 2 ways to do that.
By the way, reality is one thing. It's a quantum wave function.
I believe so, yeah.
So how do we? It appears that there are maybe a couple of hundred people in this room. It looks like distinct entities, chairs and tables and so forth. You're saying all of this is a manifestation of the quantum wave function.
That's right.
Okay.
And if I was given a footnote on my one sentence, I would have said, of course, I don't know what reality is, because nobody knows, but this is our best current approximation. And the best way to explain what a quantum wave function is to forget that we know what a quantum wave function is, and imagine that the world is, as you say, like the manifest world, right? Like here you are, here I am, etc. You see things, you see stuff, different points in space, and that's roughly the classical way of talking about the world, the way that we had before quantum mechanics. Then quantum mechanics comes along and says, no, no, no. This idea that there's something over there and there's something over there, this is just an illusion because you don't see the whole reality. And the quantum wave function says for every possible arrangement that you could think of for all the stuff in the universe, there is a probability that's how the universe will look when you look at it. And so the quantum wave function is an assignment of probabilities to all the different possible ways you could think the world could be.
It sounds strangely like a mathematical entity.
Well, it needs to be,
It's not
right?
stuff, right?
Yeah,
Well,
it's
okay,
not
okay.
stuff.
So are you
Shouldn't be
giving me a mathematical description of reality, or is that the real thing?
I-
Is the world a quantum wave function? And if so, you're saying the world is a mathematical object. Where do mathematical objects exist? Do they exist in space and time? Do they exist? Are they mental objects? Are they? I mean, normally the medium of mathematics is the mind. Mind of God, to pander to religious people. Do you want to touch any of those issues?
Look, if it's really all of reality we're talking about, I think that it would be misguided to think that it exists in anything. You know,
Right.
We describe the world mathematically. I would say that the world is the world. This statement that the quantum wave function exists in a certain mathematical structure that we call Hilbert space, after David Hilbert, one of the famous mathematicians of the 20th century. It evolves with time. These are all our human words that we use to describe the world. It's what we call an isomorphism. This little mental, mathematical, formal structure seems to match on to the world, and therefore we say that's what the world is.
Yeah. So to be precise, when I see you sitting there, I'm not seeing an entity called Sean Carroll. I'm seeing that the vector that describes the state of this thing called you, the universe, is in a certain region of Hilbert space. By the way, Hilbert space, it's much worse than the space that we live in. It has infinitely many dimensions. So
It's a big place.
yeah, yeah. And it's fun to, I mean, you know, it's great. The next time you're at a cocktail party, casually drop Hilbert space in the conversation. You'll seem very, very sophisticated.
Oh, yeah. Potential love interests love that when you talk about the Hilbert space. Well, I think, one of the crucial things about the world is that it comes to us in layers. You know, we don't look at the world, like you say, and see a quantum wave function. We see people or whatever. And what that means is that there are different vocabularies that are appropriate to describing the world given different levels of description, different levels of precision.
But you're not really a relativist. I mean, when you talk of different vocabularies, that's usually a nice, warm, fuzzy way of saying, the world is, it's not just the scientific world, it's the Lebenswelt, the world that we live in, and the moral world and so forth. But you think that all of that depends on this quantum wave function, which is a very mysterious entity.
Some vocabularies are more comprehensive than others. And I think that the deepest level, the level that as far as we currently know, is the bottom one, is the one where the world is a quantum wave function moving in this Hilbert space,
So it's interesting that science, what we expect from science, we expect it to be a way of predicting our experience, of controlling nature, giving rise to technology, but also to understand the world and to provide. We might hope that it would provide a metaphysically compelling or luminous or coherent picture of the world. And it seems as though, if you look at the history of science, go back to Newton. Newton's world was a world of good solid particles moving around under forces, and the solidity was sort of built into the conception of the world. It was like this chair seems, well, this is certainly solid. There were weird things in Newton's conception of the world. For instance, gravity was a force that somehow reached across empty space from the sun to a planet. And Newton's contemporaries wanted to explain exactly by what mechanism does gravity reach out from the sun and control the movement of the Earth. And Newton said, what was the non fingo hypotheses or something like that. I don't make hypotheses. This theory of gravity works. It predicts the motions of celestial objects, of terrestrial objects, and we'll leave the metaphysics to Leibniz, I guess. So, but at least, I mean, that the Newtonian picture of the world, or the Aristotelian picture of the world, going back to the Greeks, was something that was, it was sort of, scaled for humans to live in. And with the progress of science, I mean, now we have scientific theories that can explain, that can predict the outcomes of experiments in particle physics down to the 11th decimal place. They're amazingly precise. But they yield an utterly unsatisfying picture of the world that we live in. And so I wonder, are we mistaking a mathematical description for reality? You sort of answered that by saying, well, there's an isomorphism between the mathematical description and the reality, meaning they have the same abstract form. Does reality have a sort of stuff to it that isn't being captured by quantum field theory?
Well, think of it this way. As you learn more about the world, as you do more and more science, as you uncover more and more facts, your observations become more precise, and you go into realms that you hadn't yet seen, distant stars and galaxies, the subatomic world, and so forth. Would you expect that as you learned all these new things, your best description of the world becomes more and more intuitive and everyday, or more and more weird and surprising? It will become more and more weird and surprising because we're looking at things that we're not trained to experience.
Right.
I think it's the least surprising thing in the world that our best current understanding of the fundamental reality of everything is absolutely abstract and distanced from our manifest experience. And part of the work of science is to match those two things up.
And it's going to get worse.
I hope so.
Yeah.
That'd
Because
be
it's got a
awesome.
lot where, look at the 20th century. It's got, at the beginning of the 20th century, reality was almost intelligible.
That's right.
And with quantum theory, there are big problems, as you know, and we can talk about this. No one really understands how quantum theory works. No one understands the role of the observer in quantum theory. And physicists have, pretty much, you're an exception to an extent, but physicists have pretty much given up on making sense of quantum theory. And the line is, shut up and calculate. It works, and don't worry about what's really going on in reality out there. So,
Space is the next thing to go, by the way.
I heard time.
No, time is here to stay.
Who are you talking
baby.
to?
I wrote a book about it. I think my little prejudice is a little side comment.
Wait a minute. I thought
time
space
is
and time were an integral whole now. What are we talking about? Space and
common
time is distinct things.
misconception,
Oh, how vulgar of me.
Yeah, you might think, because Einstein said so, that space and time are actually just two different aspects of the same underlying thing called space-time. In quantum mechanics, quantum field theory, our best quantum description of reality, time plays a separate fundamental role, and the fact that it can get mixed up into space is a higher level emergent phenomenon. And I think that space is going to be shown to be just a useful approximation.
Right, but time is fundamental.
That's my personal best guess.
Okay.
I would not, bet even money on it, but that's
Right.
what I'm suspecting is true. 100 to 1 odds, I will take your money.
So let's move on to what's become a shtick of mine, the mystery of existence. The question, why is there something rather than nothing, which excites a lot of philosophers, a lot of physicists. William James, the great American pragmatist philosopher of the 19th and 20th century, called it the darkest question in all philosophy. Martin Heidegger said it's the deepest, farthest reaching, most fundamental question we can pose. Its hidden power grazes us all when we're bored. The world seems, de trop and pointless, and why does it exist? And in moments of extreme happiness, it's transformed and numinous, and the weirdness of existence strikes us afresh. And I'm getting caught up in this poetic rapture here. And the British astrophysicist Sir Bernard Lovell said pondering it can tear the mind asunder. I'm obviously a little unhinged by it after contemplating it for 6 years. And it's the last bastion of religious orthodoxy against creeping scientific secularism. You all are probably aware, while I was writing my book, why does the world exist, which seemed to me a rather esoteric, abstract question of interest to the happy few, not to the masses. I was shocked that on cable TV suddenly, on cable news show, the question, why is there something rather than nothing, was getting bandied about. And the reason was the emergence of what are called the new atheists, people like Richard Dawkins, my late friend Christopher Hitchens, and others, Daniel Dennett, I suppose. And when their critique of religion, a very fierce critique of religion, was presented, people who wanted to defend religious orthodoxy said, wait a minute, science can explain the emergence and diversity of species, it can explain the celestial motions and what's going on in the atom, but it can't explain why there's a world at all. And so when Christopher Hitchens would appear on Fox News, Sean Hannity would say, well, look, Christopher, if you don't accept there's a God, how can you explain why the world exists at all? And Laura Ingraham, one of those leggy right-wing blondes, said, you know, the whole universe came out of nothing? That defies logic and reason. You know, what was happening before the Big Bang? I remember Christopher said, I'd love to know what was happening before the Big Bang. but he really didn't have a good answer to it. And I thought, you know, we secular humanists, I'm a sort of I was raised a Catholic, I'm an atheist now. I'm sort of nostalgic for religion. I don't know about your beliefs, you probably don't want to talk about them, but anyway.
I'm very happy to talk about that.
Okay, yeah.
But
there should be a better answer than to just say, well, the universe is a brute fact. And that's what, you know, that's been the standard response if you don't believe in the God who said fiat lux and suddenly the Big Bang was unleashed. You just say, well, it's just a, you know, blind chance. The universe just popped into existence, or if you think it's eternal, it's always been here. There's no further explanation. It's quite literally absurd. You know, Bertrand Russell, when he was debating a priest on the BBC, and was challenged at this point, said, I should just say the universe is there, and that is all. So another possibility is a science maxim. But what do you think? Do you think it's astonishing that there's a world at all? And do you think that science has any role in addressing this you know, either deep mystery or perhaps it's a pseudo question?
right, I think that it's mostly a pseudo question. I do think that there's two aspects to the pseudo question. One is the scientific aspect, the philosophy, the physics, the cosmology, the Big Bang aspect, and that's the easy part.
Yeah.
And then there is the more philosophical, linguistic aspect to the question. So if you say, why does the world exist? It sounds very similar to saying, why are we having this conversation right here? And if you said, well, so why are we having this conversation? Well, we thought that people would be interested in talking about the fundamental nature of reality and the origin of the universe. And that's one possible explanation. But if you think that that's the explanation, that's the answer, that's the reason why, it's because you think that if that weren't true, if nobody were interested in these questions, then we wouldn't be having this event. So you say a reason why is something that is a necessary condition for something else to happen. But then some wise guy, some philosopher says, well, are the reason we're having this event because Los Angeles was not destroyed by an earthquake yesterday? Yeah. Because if it had been, you wouldn't be having this event, right? Is the reason why this event is being held is because space-time is four-dimensional, because life arose on Earth 4 billion years ago. There's a whole bunch of true things that if they were false, this would not be happening. So the reality is that when you ask this question, why are we having this event, there's a context. There's a set of things you accept. You believe that the world exists, the laws of physics are what they are, the history of life on Earth is what it is, the history of our actual local environment is more or less what it is, people's interests are what they are, and then within that context you say, the extra fact that people like talking about, the nature of reality, explains why we're having this event. Now you try to do the same thing for the question, does the universe exist? But there is no context. There's no such thing as, you know, the gods are sitting around and every Tuesday they decide to make another universe and they decide to make this one and they, you know, why they did that universe? Well, you know, Athena was in a sort of obstreperous mood that day and, you know, the kinds of, I would argue that there is no possible explanation that makes sense that would count as an answer to that question. And instead, what you should be doing is saying, what is the best understanding of the universe that we can have? Is there a theory? Is there a model? Is there a formalism that is complete, that includes the origin of the universe or the eternity of the universe or whatever? And at the bottom, sad to say, it might just be a brute fact. And you don't get to complain about that. You just have to accept it.
But I want to complain about it. You know, it's bad enough that there's no purpose. There's no purpose to existence. No purpose and no meaning now,
Yeah.
no reason. But it's interesting that the physicists like John Archibald Wheeler, who had a slightly mystical tendency in his thought, believed that, among other things, that consciousness was a crucial part of reality. Consciousness is apparently something that evolved, well into the existence of the observable universe. It's been around for the new estimate is 13.8 billion years.
Yeah.
Before that, it was 13.7 billion years, and it was just revised a month ago. And oddly enough, whenever I mention that fact before an audience, there's always laughter, except with this audience. And it's always puzzled me why
Los Angeles
that.
audience. They know
Yeah.
They know their
Yeah.
error bars.
Are they waiting for the laugh lights to go? Yeah. But so this quotation that struck me, I don't know where I came across it. John Archibald Wheeler, who, by the way, was the teacher of Richard Feynman. I think he coined the term quantum foam.
Black hole is his
Black
famous
hole. Okay,
point.
black hole. Yeah, right. I was. He said, how come the quantum? How come the universe? How come existence? When I was talking to Steven Weinberg, who could be called the father of the standard model standard model of particle physics. Steven Weinberg, one of the greatest living physicists, he won the Nobel Prize for his work in unifying the electromagnetic force with the weak force. Those are two of the four fundamental forces of nature. And the point, what physics, I don't know why I'm saying this, you should be saying this, but the holy grail of physics is to find a single mathematical framework that would describe all four of the fundamental forces of physics, the gravity, the electromagnetic force, the weak nuclear force, the strong nuclear force, and make them all out to be manifestations in a sense of a single underlying force. Anyway, so Steven Weinberg, who helped make one of the steps towards this goal of physics, is himself quite interested in the mysteriousness. It really, it resonates with him viscerally that the world should exist. And he said, even when we find the final theory of physics that will unify the four forces and tell us, what was going on before the Big Bang and that sort of thing, it will leave an irreducible mystery. And that's why this theory, the mystery of why this theory should describe reality, rather than reality being sheer nothingness. And by nothingness, he means, no matter, no energy, no space, no time, no consciousness, nothing. So nothingness to Steven Weinberg was a coherent alternative possibility for how reality might have turned out. And so I appreciate the subtlety of your argument having to do with context for why questions and so forth. Nevertheless, reality turned out one way rather than another. That doesn't suggest that we should at least look for an explanation?
Oh, I'm happy to have people look for explanations. What we called the quantum state, the ultimate reality of the universe, there might be something underlying that. There might be something more comprehensive and fruitful. There are physicists who sometimes, in moments of weakness, say, well, maybe the ultimate laws of physics had to be that way. Maybe there just isn't any alternative. I think that's manifestly wrong because I can think of a million alternatives before lunchtime. So,
but by the way, Einstein cherished the hope that somehow the laws of physics, he said, did God have any choice in how he created the universe?
That's right.
When Einstein invoked God, he was being very metaphorical. It was sort of Spinoza's God, which is just nature in its most beautiful aspect. But the hope that there would be a single logically consistent set of laws of nature that would describe a unique reality, which seems it's hopeless because the theory of nothingness describes the possible reality.
Right, and usually when I'm disagreeing with Einstein, you should stick with Einstein, but I nevertheless believe that he was wrong about this one.
Yeah.
And so if they're not unique laws of physics, then maybe they're the best in some way. Maybe they're the simplest, or maybe they're the only ones in which there are cupcakes, or there's all sorts of metrics you could imagine on the space of possible laws of physics in which ours are the best. Even if that were true, it would still be a brute fact that was the kind of laws we had. So you can hope, you can look, maybe I'm wrong and maybe you'll find it, but you can't demand. You can't say it must be that there is a better explanation than the fact that it just is that way.
So, some of your colleagues, physicists, have actually risen to the challenge of trying to give a purely scientific explanation of why there's a universe rather than a blank. And one of them is rather famous now, is Lawrence Krauss, who wrote a bestseller called A Universe from Nothing, why there is something rather than nothing. He has the answer. It's not actually his answer. I don't believe that the ideas aren't original with him. But basically, he believes, let's look at the old Judeo-Christian equation. The idea is that God created the world ex nihilo, out of nothing at all. Before Christianity, in fact, before the 2nd or 3rd century after the Common Era, after Christ, the idea of nothingness as an alternative reality really wasn't envisaged. I mean, the Greeks didn't think of the world as arising from nothing. They thought of it as arising from a pre-existing chaos. And so to get from chaos to a world, it was a matter of ordering the chaos and making the chaos into cosmos. But in early Christian thought, the idea was that God is so powerful, he could make the world out of nothing at all. He didn't need any pre-existing material to fashion it out of. And so the standard formula, which really underlies Western metaphysics up until modern times, is God plus nothing equals the world. Now, so what happens when you take God out of that equation? You have blank plus nothing equals the world. Well, you might hope to fill the blank with science, with the laws of nature. And this is precisely what Lawrence Krauss and other physicists, another one is Alex Vilenkin, have tried to do. So the laws of physics take the place of God in a sense. And they mandate that out of sheer nothingness, a little seed of a universe spontaneously fluctuates into existence through the mysteries of quantum mechanics. And once the seed is in place, it's a little patch of false vacuum that's, I think it only has to be about 100 trillionth of a centimeter, something like
very
that.
Tiny.
Yeah. Through the equally alluring mysteries of inflationary cosmology, it will blow up into the universe we see around us today, hundreds of billions of galaxies consisting of hundreds of billions of stars, and that's just the observable part. That's just the tip of the iceberg. And so Krauss thinks that he has solved the problem of existence. He's shown that he's done for existence what Darwin did for life, and Richard Dawkins endorsed this claim.
Yes.
There are obvious problems with this it's an interesting bit of speculative physics, it seems to be, but great problems with it as a bit of metaphysics. And maybe I've been babbling on now for a long time. I know what those problems are. Do you?
Yeah, so like I said at the very beginning, there's two aspects to this problem of existence, the physics aspects, which are the easy ones, and then the linguistic/philosophical ones. And the secret to reconciling what Lawrence and other cosmologists say with what we've been talking about is that Lawrence and other cosmologists could not care less about the big existential question about why these laws of physics, are they unique, are they the only ones, why is there something rather than truly an absence of anything at all. They're interested in the down-to-earth physics questions. They say, okay, we have the laws of physics. We're not asking why are there laws of physics. We're saying, given the laws of physics, could we sensibly describe a model in which there was something you would call nothing, and it evolved into something you would call something. And the wonderful news is that the details remain to be filled in, but that's a very plausible story we can imagine telling. I've already said, what is a quantum state? It's you give me every possible arrangement of stuff in the universe, and there's some probability I assign to it. And in that quantum state, one of the possible arrangements of stuff might be there isn't any stuff. And in fact, general relativity, Einstein's great theory of gravity, says that even the background, even the framework, the space and time through which all the stuff is distributed has a life of its own. It moves, it responds, it's dynamical. It can grow, the universe can expand, it can shrink, it could have been very tiny. So there in the quantum wave function, there is a particular option that says there is no stuff, there is no space, there is no anything. And that can evolve according to the laws of quantum mechanics into something in a consistent physical way. Now, that doesn't answer the why is there something rather than nothing question, but given a very particular definition of nothing, it can explain to you how that particular version of nothing evolved into the something we see all around us.
Yeah, right. But that's a much more modest assessment of this project. I mean, I think as physics, as speculative physics, is quite fascinating. But Krauss actually believes that he has shown that literally how something can come from nothing. And my misgiving about that is that the nothing that he starts with is the quantum vacuum. Vacuum, it sounds like nothingness, but the quantum vacuum is actually a very complex and structured thing that's governed by laws, and it's a physical object. And Krauss said, well, I've shown that something, or physics has shown that nothing is something, which sounds very much like a contradiction to me. And of course, if you start with a contradiction, you can derive anything. That's called, what is it in Latin? Come on, you were a classicist.
My Latin is a little, I was a public school kid. What are you talking about?
In the American sense.
Lucky I can add.
Yeah. By the way, he's not entirely jesting. I think physicists are terrible at arithmetic. Yeah, they disdain, the only numbers you care about are 0, 1, e, and pi, pretty much. Infinity, yeah.
So no, I completely agree.
Yeah.
I think that there's a little bit of sleight of hand here, that for an appropriate definition of nothing, which is not the one anyone had in mind, modern physics can explain how something arrives from nothing. And then they can try to convince you that the definition was good. But the thing to do in this situation is not to argue whose definition is right. It's just to be very clear about what we can and cannot do. We can very plausibly give you, or at least we're trying to construct, a complete and self-contained theory of the entire history of everything. That is not a very modest goal, and it would be great if we could do it. And it doesn't need anything outside. It doesn't need anything to start it. It doesn't need any other explanations, any extra brute facts to hold it up. It does not need anything to sustain it and keep it going. It's what there is, what there was, and what there ever will be. And the other question was, why is it that, rather than something else? And that is a question for which I would argue physics has precisely nothing to offer.
Right. And Steven Weinberg would agree with you. The question then is, do you stop talking about it, or do you move on to philosophy? But first of all, to go back to Krauss for just a second, I always attack Krauss from the left, as it were, from the more militant atheist side. I think he's still enthralled to Christian metaphysics because he believes that the equation God plus nothing equals the world, when you take God out of it, the equation is still there, and science has to deal with it. Why this assumption that nothingness is sort of the ontological default option of reality? That's very much a vestige of a Christian way of thinking. And the second mistake I think he makes, and physicists tend to make, is they see the laws of quantum field theory, the laws of nature, as being akin to divine commands. They have some sort of power over reality. Even Stephen Hawking was perplexed about this when he came up with an early model of the cosmos that showed it to be causally self-contained and self-consistent. It didn't have a beginning or an end. It just sat there. It didn't need a god or a creator. It was described by these equations. But he said, wait a minute. What breathes fire into these equations and makes a world for them to describe? Why does the universe go through all the bother of existing? And to get back to John Archibald Wheeler, I've heard the anecdotes, and he said, you take the best scientific theory of reality and you write it down on little scraps of paper and put the little scraps of paper on the floor and say, now fly. And they just sit there. They're just equations. And I think, to Krauss, they are like divine commands, and they command the abyss to give rise to a universe. And that seems to be a very primitive way of thinking. But that leads to the question, what are the laws of nature? Is it a mistake to call them laws? Yeah. You can't, if you violate one, it's not a law anymore. That's not a very good law.
That's right. So, the reason why physicists tell each other, shut up and calculate, is not because people should, as some general rule, shut up and calculate. It's because physicists should shut up and calculate. Because physicists are really bad at doing philosophy, and they like to, think that they're pretty good at doing everything. But there's a whole separate set of questions. I think that it is a separate set of questions. What physicists are trying to do is figure out what the laws of physics are and what the history of the universe is. And the status of those laws as separate things or commandments, or are they simply patterns that happen to exist? Does it even make sense to contemplate the idea of violating a law of physics? I don't know. I suspect that these are also not the right questions to ask, to be perfectly honest. It is a fact. We don't want to, when you say that there are facts you just have to accept about how the world works, it's a very dangerous weapon in your arsenal, because it's probably true that there are some facts that that you just have to accept about how the world works. But you don't want to prematurely shut off the possibility that there is a deeper explanation. My favorite law of physics, the second law of thermodynamics, the fact that entropy and disorderliness grows with time. In the 19th century, that was a fact. That was a law. We couldn't imagine changing it. And when Boltzmann and Gibbs and Maxwell came along and said, well, if you believe in atoms, then I can explain why there's a second law of thermodynamics. And furthermore, it's not even a law, it's just a really good idea. We can imagine violating it in certain special circumstances. So all of which is to say, I don't want to rely on the brute fact, just accept it excuse too quickly, but it's absolutely clear that at some point you will have to accept that, and the laws are things that we see nature obeying. They're not laws like a legislature gives you. They're patterns of reality that we try to tease out.
So you think they're merely higher level descriptions of what goes on in the world, not things that somehow exist platonically apart from the world and control the way the world works. And
my attitude would
completely
be,
agree
I
with you.
truly don't know what it would mean to say that a law of physics exists in addition to the world.
Yeah. By the way, since we're going to get onto the topic of time, I'm going to look at my watch rather ostentatiously to see how we're doing. Oh, good. Actually, I've yet to get to the really sexy material.
We have 3 more hours,
yeah, there's
right?
a lot of juicy stuff. Yeah. Okay, I want to, by the way, Steven Weinberg himself, the father of the Standard Model physics, he is, by his intellectual curiosity, by his Lower East Side Jewish intellectual, DNA, he wants to go further. And he said, I take seriously something called the principle of plenitude. I think that's how he put it, or the principle of fecundity, a principle of fullness, which says that the world that we see around us, governed by this particular set of laws, quantum field theory, is just one possible reality, and all other imaginable realities are actual. There are universes that are governed by completely different sets of laws. There's a universe that's nothingness, the null world that really exists according to this principle. So his answer to the question, why is there something rather than nothing, is there's not. There's both. There's something and nothing. There's this null world. That I have problems with that too. But I think it's interesting that even a hard-headed physicists like Steven Weinberg would be driven in this rather extravagant, flamboyant metaphysical direction to take seriously an idea that it actually goes back to Plato. So maybe when ideas are around for a long time, that means they'll be around for a long time. And so maybe 1,000 years ago, people will be talking about the principle of plenitude, calling it something more fashionable, up to date, and quantum field theory will be looked upon as sort of medieval Aristotelian physics, for all we know.
It's possible. The great thing about science is we are not done yet.
Right. But that too is controversial. But I agree with you. So let me ask you. Okay, let's move away from philosophy into let's play in your little park of physics, and I want to ask you as a physicist to respond to another question. As a physicist, what would you say is the form we should expect the universe to take?
I wouldn't expect the universe to take any form.
Okay, what's the most probable form it should take?
You
know what I'm getting at. Come on.
No, I kind of want to unask
Don't
those
be coy.
questions. I mean, I would need.
You don't want to. You asked the question on page 272 in this marvelous book.
What we need to do is to allow ourselves a context. So if we have a context, so I mean
the most natural context. I'll grant you the need for context. Give me the most natural context.
So imagine that the world is some collection of stuff, and described by a quantum wave function, some degrees of freedom, as we call them in physics, just to include the possibility it might be fields, it might be particles, whatever, but there's some quantum mechanical description of reality. And one of the nice things is, so there's many different configurations that we can imagine, right? Many different arrangements of the universe. And we're actually allowed to count. We're allowed to say, well, most configurations look this way, very small fraction looks some other way, and so forth. And so if all you knew were the laws of physics and the particular kinds of stuff, if that's all you knew, then I think that by construction you would say the most probable arrangement of the universe is the most typical one, the kind of arrangement that most of the states of the probability space find themselves in. And the reason why this is even worth talking about and is even mentioned in my book is, of course, the actual universe is nowhere near that. The actual universe started out, given the degrees of freedom that we have, the particles and forces that we know about, in a fantastically, unimaginably unlikely part of the space of all possibilities. And to a working physicist, what this means is there's something we're missing. There's something that we don't understand.
May I interrupt just for one
Sure.
second? Tell us, though, what is the most typical form that the universe should take according to this?
Yeah, so we don't know is the short answer. My
No, but you have a very good conjecture in the book.
Well, I have a conjecture.
What's the
right, so
highest
I'm going to
entropy
explain
state?
the conjecture.
Yeah, okay.
It's empty space. Why would it be empty space? Well, you know, of course, because you've read my book, that there's something called the second law of thermodynamics. Entropy increases, right? As time goes on, the universe gets more disorderly. And the mathematical statement of that is that as time goes on, the state of the universe becomes more and more typical. It looks more and more like the most probable state it could be in. So if you want to know what is the most probable state the universe could be in, just ask, where is the universe going, right? Look towards the future. And in 1998, we found that not only is the universe expanding, it's expanding faster and faster. It's not slowing down. There's no sign that we'll ever recollapse. So what will happen over the course of time, the universe is about, to an order of magnitude, it's 10 billion years old. It's really 14, but okay, 10 is good enough. 1 quadrillion years from now, all the stars will have burned out. They'll have used up their nuclear fuel. They'll fall into black holes. But those black holes will radiate. So 1 Google years from now, 10 to the 100, Google in the good old-fashioned
G-O-O-G-O-L.
Before
Yeah,
the computer people messed it up.
G-O-O-G-O-L, not G-L-E.
That's right.
That's the real Google.
1 Google years from now, all of those black holes will have evaporated. And all the particles from those evaporations will have spread out to the 4 winds of the universe, and space will continue to expand, and there'll be nothing left but emptiness, empty space, and that will last forever, as best we know. So the most probable state to find the universe in is, if you pick the state of the universe out of a hat of possible states of the universe, empty space, nothing around.
Right. So the most probable state of the universe is almost nothing. So why is there something rather than nothing?
You should write a book about that. That's a very good question. So in the context, in this context, now we have a context. We can say, okay, given that that's the most probable state of the universe, could we imagine that somehow, just through the laws of physics, out of that comes a universe like we see? And the answer is maybe. We're trying. We don't have the final answer to that yet. It's in the end of the book. Right? Yeah.
By the way, you don't mean totally empty space.
I don't. I mean, as empty
and they're
as
very.
it's
And
possible
tell
to
us
be
about the fact that you might be a Boltzmann brain.
Right. This is really. There's a quote by Carl Sagan. He says, in order to make an apple pie, you must first invent the universe. And according to our best current physical understanding, he's not right. So what he means is, to make an apple pie, you need apples, you need sugar, you need flour, which means you need apple orchards and plantations, which means you need the earth and a biosphere and the sun and the galaxy and the universe. But it turns out if you play this game of just considering all the different arrangements of stuff in the universe and watch them evolve and ask, of all the ways that the stuff of the universe could come together to make an apple pie, what is the most likely thing that could happen? The answer is you have empty space with some little background, not very noticeable quantum fluctuations, right? Because quantum mechanics says you can't pin even empty space down to perfect quietude. There's always like the possibility that you see a particle when you look there. So the empty space is just jiggling around in its quiet quantum way, as empty as it could possibly be, but suddenly assembles as a really, really unlikely collection of quantum fluctuations, an apple pie. And of all the possible ways to make an apple pie, it is much easier to do it that way than to first assemble the whole universe. And this is nothing speculative. This is bedrock accepted statistical mechanics. And people would nod and go, that's a funny way of making an apple pie. But then you say, okay, what about this room? What about the fact that here we are, we know some things about the room, I see you, you see us, and there's everything, every piece of macroscopic information we have about this room. So here we are, we're people, we have memories and feelings and the states of our brains and so forth. And we say, of all the ways the universe could make us here in this room, we have the impression that somewhere out there there's something called California and Los Angeles, and somewhere else there's even New York and so forth. Of all the ways that the universe could bring us into existence, the same thing is true as with the apple pie. It's much easier just to randomly fluctuate into this room than to first to create a universe. It's much easier to randomly have the idea that California exists fluctuate into your brain than to actually make California. And so if you ask what are the most common observers in the universe, they are brains. They are random collections of stuff that came together to make a conscious set of atoms and molecules that just sort of is aware enough to look around and go, empty space, and then die. And that's called
not even look around though. They have the thoughts that they're looking around. They have no actual eyes or person. So that raises the question: how do you, since that the most probable explanation for the experiences you're having right now is that you are a Boltzmann brain that is randomly fluctuated into existence very briefly in otherwise empty de Sitter space. I just wanted to just yeah. How do you know that that's not what you are?
Right, and this requires fundamentally a philosophy argument. So there's two steps to the argument. How do we know that this room did not just fluctuate? Or, it's the same question at the philosophical level as saying, how do you know you're not in a computer simulation? How do you know that you're not being taunted by an evil demon who's putting false impressions into your mind? In the case of the Boltzmann fluctuations, Boltzmann is the great 19th century physicist who invented this formalism of things fluctuating and so forth.
And committed suicide.
Everyone who works in statistical mechanics ultimately commits suicide.
All great logicians also commit suicide or are crazy.
Right, that's right.
Yeah.
Become a writer. They never, so the point is, well, what if it were true that we just fluctuated randomly, that there is no such thing as California, that your memory of what happened last week is just a random fluctuation in your brain? So what if that were true? Well, if that were true, then all of your purported knowledge about the laws of physics, the rules of logic, the way that we make true deductions from data and so forth, they just randomly fluctuated into your brain also. So even if it were true, you would never have any right to believe that it were true. So it's what we call cognitively unstable. It can never be both justified and true at the same time. So the other way out is to say, well, maybe it's not true. Maybe there's something else in the laws of physics that we're missing. We are not a typical state in de Sitter space, in this future empty space with some energy in the vacuum. Maybe the cosmological theory we have needs to be improved, and that's why they pay us the big bucks.
Let's see, we have about 5 minutes left. So let's talk about time a little bit.
Okay.
There are two things about time that are rather salient in our experience. One is that it has an arrow. The past is different from the future. Another is that it seems to have a flow that we're sort of, it's like it's like a river. It flows in one direction, but it seems to flow with a certain speed. And there are slow areas, and then there are rapids, and it's all leading to this, the termination of empirical experience or death. We're being rushed along willy-nilly towards our death. Now, the arrow of time, it has a physical explanation, which you've described very lucidly in this book. How about the sense of time flowing? Is that an illusion? Einstein thought it was an illusion. It's certainly, it's probably the most, to our lived lives, it's the central fact. Is it an illusion? And if so, should that be reassuring to us?
Well, I never use the word illusion when referring to things that we find to be useful in our description of reality. I mean, we described this room, the air in this room, in terms of a temperature. Boltzmann and his friends said it's really not a temperature, there's just molecules bumping into each other. But I don't think that the temperature is an illusion. I just think it's an appropriate term in the higher level description. I think that the flow of time is a perfectly valid way of talking about our human experience. It's not something that is there in the fundamental laws of physics. I think that the impression that time flows is absolutely simply a consequence of the physical arrow of time. The fact that we exist at every moment, but in every moment the entropy of the universe is a little bit higher, or more relevantly, at every moment the entropy was lower in the past. And what that lets us do is our present state lets us reconstruct what was going on in the past. That's why we think that the past is fixed. It's in the books. It's not something we can change. Whereas the future, we think we can make choices about it. This idea of making choices and having some sort of strong libertarian free will, again, nowhere to be found in the fundamental laws of physics, but a perfectly good way of talking about our existence as human beings. It's because the future of the physical universe has no such constraint as having been low entropy in the past that we feel that we have the right to make choices and influence it. And I think the flow of time is the same kind of thing.
Yeah. And the flow of time obviously has to do with the fact that our memories accumulate in one direction. We have memories only of the past. We have no memories of the future. And the odd thing is that that is explained by the fact that the universe began in a very organized low entropy state.
Yes.
So, which is astonishing. This existential fact about our existence goes back to a mystery of why the Big Bang had this immensely improbable low entropy, organized state.
That's
By the
right.
way, how many Googles of entropy do we have going just about now?
Oh, it's more than a Google. It's a Google to the 20th power.
No, it's 10 Googles.
10 Googles is
10
approximately
to the 101st,
one Google.
10 to the 101st, 10 to the 101st power.
Yeah, which
Yeah,
is
yeah.
pretty close to 10 to the 100. Oh,
Yeah,
you
no,
mean the
it's-
present value. I'm sorry.
Yeah,
the
10
present
yeah,
value,
yeah, yeah.
not
Yeah.
okay, not
Yeah.
the ultimate value.
I'm
You're
sorry.
right. I was
Yeah,
just
yeah.
giving a different number. 10 to the 120 is the
Yeah,
the
that's
biggest
yeah,
it
yeah,
could be.
yeah, yeah. So we're a
You're
long
right.
way from there,
Yeah,
but we're
10
a
or
long
so
yeah,
Googles
yeah.
among friends. Yes. The analogy I like to give is the first question that is interesting. The question: why do you even need to explain why the past is different from the future? Why is that an issue? And it's because the modern laws of physics, where modern means since Isaac Newton, have erased the difference between the past and the future from our laws of physics. It's nowhere there in the fundamental laws of dynamics. Just like there's no fundamental arrow of space. If you're here in the room, that you can tell up from down, but if you were out there in space in your little spacesuit, there'd be no difference between up, down, left, right, backwards, and forwards. And so the modern understanding is that just like the explanation for the arrow of space here in this room is that we find ourselves in the vicinity of an influential object, namely the Earth with its gravitational field, the explanation for the arrow of time is that we find ourselves in the vicinity of an influential event, the Big Bang, 13.8 billion years ago, that set up the low entropy of the universe.
Do you think the universe is eternal?
My guess, again, even money, yes, the universe is eternal.
Into the future, but how about into the past?
Both ways.
Really?
Be ashamed
Okay, no,
to
that's
have it
interesting.
end.
And by the way, I hope that's true. I think that makes it much more. It's metaphysically much more satisfying. But it's controversial. Vilenkin, Alan Guth, who was one of the original fathers of inflationary cosmology, and a third guy,
Bourdet, yes.
Bourdet, came up with an a priori argument proving that the universe has a finite past.
Yeah,
and we don't want to
that.
get into that. But I mean, this is
Except,
fascinating.
I got to say that's not true.
They think it's true.
No, they don't. In fact, Alan agrees with me. Alan Guth and I are writing a paper saying that the universe could be eternal. Alex Vilenkin
This is like fashion. I can't believe how
like,
frivolous you
better
guys
keep
are.
up, you know? That is so 2011.
Yeah.
Point of view. Summer 2011.
Yeah.
So no, I mean, you can't come up with an a priori argument because you need to make some assumptions. They make some assumptions, and they show that under some assumptions there's a singularity in the past. And then the question is, what do you do at a singularity? Do you push through? Do you say a singularity is merely an obstacle to our classical way of thinking about the universe, or is a singularity really a boundary? Is it really the start of the universe? And
That's not the argument I was thinking of, by the way.
Well,
Yeah.
okay.
Okay, go ahead.
That's
Keep
exactly
going.
what
Sorry.
we don't want to go into.
Yeah.
But my 5-cent argument for the eternity of the universe is that once you think the laws of physics can take us from yesterday to today and from today till tomorrow, it's easier to let them take us from minus infinity to infinity than to put a boundary past or future.
Yeah. Actually, these people probably have thoughts that are more interesting than these last few propositions
haven't
that
answered
you've
all
been
their
asserting.
questions yet?
Yeah, but actually, I should say that the elephant in the room that we haven't commented upon is the multiverse. The multiverse is, I mean, actually, you use that. I mean, the multiverse does wonderful things. It explains why our universe seems to be fine-tuned for the emergence of life. You invoke it to explain why the Big Bang started off our universe in a highly organized state. It's actually, but there are independent reasons to believe in the multiverse. You're not simply inventing it to solve your problems,
Exactly,
but it really will solve all your problems. So, I mean, there's a self-help aspect to this. It explains why we live one way in time and why we're being rushed to the grave. Did I vulgarize it in putting it that way?
No,
did.
I think, I mean, the multiverse, a little multiverse goes a long way, is my
Yeah, but then why do you keep inventing so many of them? There's the inflationary multiverse, and you believe in that, and you believe in the quantum multiverse. And so if we had another 2 or 3 hours, I would love to discuss how the inflationary multiverse and the quantum multiverse fit together, and are they the same thing? But alas,
if they like us, they'll have
life
us
is
back,
too
so we
short.
can talk about that,
Yeah. So let's open it up to some questions, and yeah.
First of all, thank you for a great conversation. My question is related to the fact that in terms of knowing the universe, we are only aware of 4% of the known energy and matter. So the dark energy and dark matter are, for the most part, just open questions. So given that perspective, what right do we really have to tackle the big questions when we don't even have the basics right so far?
Yeah, so the background for this is the idea that since the late 1990s, cosmologists think that they have the inventory of what the universe is made of. It's about 4% what you call ordinary matter, which is every particle ever discovered in any physics experiment ever. About 26% is dark matter, so another kind of particle, another kind of stuff, but nothing that has appeared in a laboratory yet. It's just some particles that have gravity that form into galaxies, but we haven't actually detected them directly. And then 70% is this stuff called dark energy, which isn't even particles, right? It's just energy smoothly spread throughout the universe. And I was once on Science Friday, and Ira Flato said, "Isn't it embarrassing that cosmologists understand 4% of the universe and nothing else?" And I'm like, we understand 4% of the universe. That's the most awesome thing ever. You got to be proud of that. 100 years ago, we understood 0% of the universe. It's not that dark matter and dark energy haven't been, found. It's that they have been touched. We haven't actually prodded at them in our laboratories. We have detected their effects. If the moon were made of dark matter, we'd still know it were there because it still would give rise to the tides here on Earth. And you could figure out the mass of the moon, where it is, how far away it is, the whole bit. But you just couldn't see it. And it's exactly the same thing for dark matter and dark energy. We know what they are, what they do, we know where they are, we know how much of it they are, we know how they evolve with time. We just haven't actually made them in the laboratory yet, although we're trying. And for dark matter, I've bet good money that it's a matter of years, not a matter of centuries, before we actually see it in the lab. This is the dark matter decade we live in right now. So,
I think you're being a little too, just a footnote. Dark matter, not a deep mystery. Dark energy, pretty deep mystery at this point, and I think we
really.
don't know how it evolves in time. Is it the cosmological constant, or is it a field that changes with time?
So
Andre Linde said we don't even know. The expansion of the universe is now accelerating, and so it looks like it's not going to be the two scenarios where the big crunch, where it expands to a certain point, and then the combined gravitational effects of matter and energy cause it to start contracting, and a fiery end like the Big Bang, except messier. The big chill, where it just spreads out more and more slowly. Now the scenario is the big crack up, where the universe literally it's undergoing an accelerating expansion, and the parts pull away from one another, to put it crudely. And Andre Linde, the father of the best theory of chaotic inflation, I think you would agree, says we have no idea how these fields that are driving the acceleration of the expansion are going to behave over time. And he said, I still think it's possible that the universe will end in a big crunch. And so I just wanted to inject that note of greater mystery into at least part. Dark matter, not very interesting. It's either machos or wimps, right? But dark energy still pretty
No,
mystic,
so
right? Yeah.
see, there's a bunch of things to say there. One is that my reference to the evolution in time was really only to the past history of the
Okay.
universe, not to the future. So we don't know what dark energy will do toward the future. We do have a theory of what the dark energy could be that is very simple, very predictive, and fits all the data, and that is the cosmological constant. Of course, it could be something more complicated. Of course, it's worth looking, and we're spending lots of money trying to figure out what the right theory is. But the same exact thing is true for dark matter. You know, we know its basic properties that it has in the universe so far. We don't know which specific model it is. But the difference is that there is this theory of dark energy, that it's just constant, not doing anything, that if that's true, and it's the winner so far empirically, it will be boring. It could be interesting, but it could be boring. But dark matter's got to be interesting. It's a particle. It's a thing you can touch and move around with. There could be dark forces. There could be more than one kind of dark matter. There could be dark atoms out there. There could be a whole intricately interacting dark sector with all sorts of new physics. It could be full employment for the next 1,000 years.
Yeah.
So
Yeah.
I think dark matter-
Reality always turns out to be
Yeah.
much more encompassing. Just when you think you've got it all, you find out it's only 4%.
And I should also say that I think in sometime later this year, maybe November, the sequel to Thor comes out, the movie. Thor, The Dark World. All I will say is that I was a science consultant for this movie, and dark matter might be mentioned.
Excellent. Okay.
We have a question over here.
Okay.
All right, thank you, gentlemen. My question is, if so far we have lived 13.7 billion years, and yet we just got mentioned that perhaps this universe is eternal, is it only eternal in the future? I mean, in other words, the universe will be expanding infinitely, and so on and so on, but that it's not really eternal going backwards? I mean, that there was nothing before the Big Bang? I'm not quite understanding this conception here.
Yeah, so I'm sure that you have your own take on it. My take is that the Big Bang might not have been the beginning. So when we talk about the Big Bang, we talk about it using the best theory we have of space and time, which is general relativity, given to us by Einstein. And Einstein says that space and time can change and evolve, and if you trace backward in time, 13.8 billion years ago, there's a moment when everything was on top of everything else, and all of the quantities in your equations become infinitely big. That's the singularity, the Big Bang. But it doesn't mean that time began at the Big Bang. It means that our knowledge ends at the Big Bang. Our ability to describe what happened fails. We know that general relativity isn't the right theory of the universe because it doesn't include quantum mechanics. So what we're saying is that there might be a better theory that we don't have yet, that includes quantum mechanics and gravity, in which the Big Bang is not the beginning, it's just a phase the universe goes through. It's a particularly violent episode in an eternal history of the universe.
And a very local episode. Big Bangs.
Very
Did
possibly,
the
yes.
Big Bang come? Does it say this mechanism operated only once? Yeah, I mean Big Bangs are going on, as it were, all the time in the
Could be,
multiverse,
yes.
and yeah.
Thanks for being here. I'm Rabbi Wendy Spears, and I have a two-layered question. You talked about layers, and there was an article in the news in the LA Times about layers and how other layers are acting on our layer of reality. And I was hoping you would speak specifically about Higgs boson, and I wanted to clarify that Jewish theology and philosophy is not Christian theology and philosophy.
I always get that wrong. I'm sorry.
I'm not exactly sure what the layers language in that question referred to in that article that you read. There's many different scientific theories that we bandy about that we're not sure are right yet. One of them says that in addition to the 3 dimensions of space that we know and love, up, down, left, right, forward, backward, there are extra dimensions of space. And a dimension in this case is not a place you can go, it's a direction in which you can move. And we look around, we only see 3 directions which we could possibly go, but maybe the others are like really curled up very tiny. And if that's true, so we are a point, our whole 3-dimensional world is one point in some 6-dimensional space. And there could be other points that are their own 3-dimensional worlds, parallel to ours, an infinitesimally small distance away from ours. And these are sometimes called branes, B-R-A-N-E-S. short version of membrane, because a membrane is a two-dimensional thing, and before physics came along, no one invented a word for a six-dimensional thing. So brain, a sixth brain, it would be a six-dimensional thing. So the world we see might just be one of a very large number of parallel brains, and maybe the dark matter lives on another brain. That's a plausible theory. And the Higgs boson doesn't live on other brains, but it has some mysterious properties. If you did a back-of-the-envelope calculation, the Higgs boson should be a lot heavier than it actually is. Maybe that's because of the influence of other brains. So that's called the hierarchy problem, and Lisa Randall, who I guess has been here previous times, came up with an explanation of the hierarchy problem by using brains. So no one can say that we're not imaginative in trying to figure out how to solve these problems, but you do need to distinguish between stuff we know is true and stuff we're still guessing at, and this is definitely in the latter category.
There's also a theory, though, by the way, that the cosmic creation events happen when two brains collide.
Yes.
So the idea that our universe came from brain damage, which would explain a lot.
It is. Every
Not my pun, by the way.
brain pun.
I always
has been
frown at a
made
pun.
in the
Yeah,
physics
yeah,
literature.
yeah. Not by
Yes,
me. Yeah,
brain
yeah.
surgery.
You
yeah.
like puns, don't you? Yeah.
My head hurts, but I'm curious if you consider what you talk a lot about the rules of physics governing much of your thinking on this topic. Are you constrained by those rules of physics? Have they yet to evolve? And are they crude tools? Or do you think something will come along in your lifetime, perhaps, that'll allow you more finesse in explaining what's going on?
Well, there are the laws of physics, and then there's our knowledge of the laws of physics, which is necessarily provisional and contingent and incomplete and so forth. Again, I don't think that a law of physics is handed down anywhere. When we use the word law, it's not exactly the right language. It's a pattern. It's a feature of nature. When we see two particles bump into each other and scatter off, they have a momentum, the two of them, before they hit, and there's a momentum after they hit. And every single time in the history of the universe we've seen that happen, the momentum before has been the same as the momentum after. You could imagine that it's different, but it has never, ever, ever been different. So we call that a law of physics, conservation of momentum. Could it be different tomorrow? Yeah, sure. I mean, there's no reason to think that it will be different tomorrow, but if data came along that would be better explained by imagining that that was changing with time, the physicists would be the first to adopt it.
May I add one thing to observation? Conservation of momentum is equivalent to the fact that the laws of physics are the same throughout space, essentially. Conservation of energy is equivalent to the fact that the laws of physics are invariant under time. And so is it possible, whenever the conservation of energy seems to be violated, what do? We find another form of energy, right, so it's not violated. And we do that because if it is violated, the laws of physics are no longer invariant under time. In a sense, they're not laws or universal anymore. So the objectivity of the laws, it could be to some extent an artifact of our own understanding. And, what is energy? As Feynman said, we talk about it, we can measure it, we don't really know what energy is. And so we do have a certain freedom to augment known energy with additional kinds of energy to just to save the conservation of energy and the invariance of physical laws under time. So I'm making this sound all very subjective and idealist, but I don't want to completely lose the subjective idealist angle because it's so much fun to think about it at 3 a.m. when you're having another bong hit,
yeah,
or sherry, a glass of sherry, perhaps.
Thought about the universe, man. But I think a concept or a rule of physics is no good if there's one new concept for every new experiment that you do. The reason why conservation of momentum is useful because it always seems to be the case. And there had been experiments when it didn't seem to be the case. A neutron out in empty space all by itself decays. It's an unstable particle. It creates a proton and electron. And when people first noticed this happening, and they measured the momentum very carefully, it didn't add up. It was not the same before and after. So very famously, Wolfgang Pauli said, well, maybe there's another little invisible particle you will never detect coming out to make momentum conserved, exactly like you said. But then it turns out that little particle, we call the neutrino, makes other predictions. If that neutrino can interact with neutrons, then it can interact with other particles. And nowadays, we make beams of neutrinos, and we detect them with incredibly high precision. So saving the phenomenon by adding new stuff only works insofar as the stuff you add is also useful in other contexts.
I've heard it said by theologists that science is the how and theology is the why. I'm just curious from your profession, if there was a deity that started the laws, would that affect your work at all? And has anything that's been discovered precluded the fact that there might be a deity at work from, your scientific point of view?
I can give mine, but you're just as expert as
I simply want to make another observation. Alan Turing, who invented the theory of computing and cracked the Enigma code during the Second World War and saved his country, and was hounded for his homosexuality as a result of that, despite that. Anyway, Alan Turing, very deep thinker, said, science is a differential equation, religion is a boundary condition, which is along the, kind of a nice epigram.
Shut up and calculate, Alan.
But yeah, you answer the substance. I give the epigram.
I would think, look, sometimes you hear it said, maybe along a similar attitudinal line, that science proceeds via methodological naturalism. That science assumes that there's nothing but the natural world and tries to explain it and is just blind to the possibility that there is God or the supernatural or the divine or anything like that. And I think that that is completely wrong. I think that science does have a methodology, but it's empirical. It's not naturalistic. Science says we will only believe in things if they are forced onto us by our observations and our data. And if the observations and the data presented us a world that could be most efficiently and successfully explained by imagining that there were a god or spirits or whatever, scientists would be the first ones to believe that. And as far as I would judge, in the history of science, for the last 500 years, everything that we've learned about the universe has moved us further and further away from imagining that that was needed. The better we understand the universe, the more it seems to explain it in purely naturalistic terms.
But
you're enjoying this so much.
Deity, yeah. No, I'm with you there. But there's a dangerous possibility that our universe could have been created by an intelligent being that wasn't a deity. And Andre Linde, the father of inflationary cosmology, described this scenario to me: the possibility that our universe was created by a physicist hacker in another universe. And it's not that hard to get a universe going. Given inflationary theory, you just need, 1/100 trillionth of a gram of matter, and you have to massage it in a certain way, I suppose. And he said that would explain, if our universe was created by a physicist hacker, that would explain why it's so crappy. Why it's a botched job.
Yeah.
My theory is that the universe, was created by a being that's 100% malevolent, but only 80% effective, and that explains it very nicely.
Well, look, these are old ideas. That all the ancient pantheistic religions did have this. They didn't think that their gods were omnipotent and omniscient. And David Hume, in his dialogues on natural religion, he has this long dialogue between the agnostic and two believers. But one believer was this sort of transcendental philosophical guy who said that God is perfect and unknowable and you can't say anything. The other was more of a natural theologian, that is intelligent design, that God made the universe and we can learn about God by looking at what the universe is. And so the other believer, says, what do you mean? Like, if you really believe that God is some sort of engineer, then you're opening the possibility that God is like a graduate student. That we were the summer project for God, that, God was a committee that didn't agree, and all these different possibilities. And the question is, what is the simplest, most powerful model of fitting the data that we have? And if it becomes necessary to include that kind of stuff, that's what we'll do.
Thank you. If one listened to tonight's conversation, one would think most of what you're trying to get at are causal statements. But in the very doing of that, you seem to be refuting the idea of causality. Time goes both ways. Apple pies are not made by bakers, but they just appear. So I wonder if you'd comment on how this kind of approach to understanding the universe affects our current concept of causation.
Yeah, I would say this is a great question, actually. And there's a lot of difficult thinking to be done to get the once and for all answer to that question, but roughly speaking, causality is like temperature. It is not a fundamental part of reality. It is a useful, higher level emergent concept. Why? Because there's an arrow of time, because the past is different from the future, because the entropy was lower in the past, and therefore our way of accounting for the evolution of the universe through time necessarily speaks of things we call causes preceding things we call effects in a very systematic way. But that is a feature of the actual macroscopic arrangement of stuff in the universe, not a feature of the underlying fundamental dynamical laws.
That's a very eloquent way to end this conversation, I would say.
Thank you very much.